Advanced GraphRAG 2, the next 5 families. Let's dig in. For 4 submodules now, you have been writing a specification, and nobody mentioned that's what you were doing. 2 clocks, 4 fields, half-open intervals, close, never delete. Every one of those is a requirement, and requirements are cheap. Anybody can put them on a whiteboard. So this part is where we go and meet something that actually implements the whole list in Python that you could install this afternoon. 2 names, Graphiti and Zep. Graphiti is an open-source Python library that builds and queries a temporally aware knowledge graph. That is the sentence. That is the whole sentence. It is made by a company called Zep AI. Rasmussen, Polichuk, Beauvais, Ryan, and Chalif are the names on the paper, and it ships under Apache 2.0, so you can read every line of it. It is not a service you call. It is not a platform you buy. It is a library you import. So what do you type? Pip install graphiti-core. 1 package. But here's the part that surprises people on day 1. Graphiti does not bring a database with it. You provide the graph store. Neo4j 5.26 or newer, or Falcor DB, or Amazon Neptune. You also provide a language model and an embedding model, because extraction and resolution are model calls. 3 systems to run, not 1. Budget for that before you promise anyone a demo on Friday. 4 object types. Learn only these and you can read the whole library. An episode is a raw unit of input, a message, a blob of text, or a JSON document, kept verbatim. An entity node is a thing the extractor found, a person, a company. An entity edge is a fact connecting 2 of them, and crucially, it is the edge that carries the dates. And a community node is a cluster of tightly linked entities with a summary. Episodes, entities, edges, communities. And the surface area you actually touch is almost embarrassingly small. You hand the client 3 things: a graph database, a language model, an embedder. And then there are 2 verbs: add episode, which is the write path, and search, which is the read path. That is the API. Everything else in this video is machinery hiding behind those 2 calls, and we are spending a whole part on the machinery because the machinery is where every interesting decision lives. Now the name confusion, because it catches everybody. Zep is not another word for Graphiti. Graphiti is the engine, the open-source library you run yourself. Zep is the hosted service built on top of that engine, where somebody else runs the database, the extraction workers, and the governance. The tidy way to hold it: Graphiti builds the graph. Zep operates it at scale. The paper we are about to quote is titled Zep. The thing you pip install is Graphiti. One more framing before we open the lid, and it is the author's own. Microsoft's GraphRAG from the first course is built for static document summarization. Batch processing, community summaries, sequential summarization at query time, basic timestamps. Graphiti is built for the opposite job: continuous incremental updates, hybrid search, and explicit bitemporal tracking with automatic fact invalidation. Neither one is wrong. They answer different questions. If your corpus never moves, you genuinely do not need any of this. The graph is not one flat pile of nodes. It has 3 tiers, stacked. At the bottom, the episode subgraph, raw input, untouched. Above it, the semantic entity subgraph, the entities and facts pulled out of those episodes and resolved against what you already hold. And at the top, the community subgraph, clusters of strongly connected entities, each carrying a summary. Bottom tier is what you were told. Middle tier is what you concluded. Top tier is what it all adds up to. Why keep the raw messages at all once you have extracted the facts? Because extraction is lossy, and the paper is blunt about it. Episodes are a non-lossy data store. And the links run both ways. From a fact, you can walk back to the exact message that produced it. that is your citation. And at 2 in the morning, that is your defense. From an episode, you can walk forward to every entity it touched. Nothing in here is a dead end. That split has a name borrowed from psychology, and the borrowing is deliberate. Episodic memory is your memory of distinct events, the meeting last Tuesday. Semantic memory is your memory of how concepts relate, that Dana Reyes runs technology at Helio Systems. You hold both, and you would be a mess without either. Graphiti holds both too. Episodes are what happened. Entities and facts are what is true. Storing only the conclusions is how a system forgets why it believes things. Here is the loop that runs on every single episode you hand it. Extract the entities and facts. Resolve them against what you already hold. Detect whether anything new contradicts anything old. Invalidate whatever it does. Link everything back to the episode it came from. 5 steps, every episode, every time. And you will notice that steps 3 and 4 are the entire subject of part 2D. So this is what that argument looks like as running code. Let's put one real message through it. Dana Reyes joins Helio Systems as Chief Technology Officer in March, and the announcement lands in your system in July. Watch what the loop does with that. It pulls out 2 entities and 1 fact. It matches Dana against the Dana it already knows. It notices the Meridian record cannot still hold. It closes that record, opens the new one, and staples both to the message that caused them. 1 message in, 5 operations out. Extraction is not one prompt. 2 details make it work. First, context. The system reads the current message together with the previous 4, so pronouns and follow-ups resolve. That is 2 full conversational turns. Second, a reflection pass, borrowed from the reflection paper. After the first extraction, the model is asked to look again for entities it missed. That second look is not free, and it is the difference between capturing a conversation and capturing every 4th sentence of one. Then, resolution, the step that quietly decides whether your graph is any good. The extracted name gets embedded into a 1024-dimensional vector, and 2 searches run against what you already hold. Cosine similarity over the embeddings, and a full text search over existing entity names and their summaries. Both feed 1 candidate list. That list, plus the episode text, goes to a language model with a resolution prompt, and out comes either a match with a merged name and summary, or a brand new entity. And there are exactly 2 ways to get this wrong, with opposite symptoms. Miss a match, and 1 Dana Reyes becomes 2. Her history forks, half her facts live on each copy, and no query ever sees the whole person. Match too eagerly, and 2 different Dana Reyeses fuse into 1 impossible individual, holding both their jobs. Splitting loses connections. Fusing manufactures them, which is the same asymmetry we found in over and under invalidation, and that is not a coincidence. A fact lives on an edge between 2 entities, which sounds limiting because plenty of real facts involve 3 or 4 things at once. Graphiti's answer is quietly clever. The same fact can be extracted several times between different pairs. Dana, Helio, and the March start date become a little constellation of edges, all carrying the same sentence. The paper calls that an implementation of hyperedges, multi-entity facts modeled with ordinary 2-ended edges, and no new storage primitive required. Steps 3 and 4 we have already done properly, so here is 1 line of recap. A model compares the new edge against semantically related existing edges, and where it finds a temporally overlapping contradiction, it closes the old one. What is new is the exact rule Graphiti writes down. The closed edge's end date is set to the start date of the edge that displaced it, copied, never computed. And when the 2 clocks disagree about ordering, ingestion time wins. Newest information takes precedence. Small but important. The 4 fields you learned in Part 2C have different names in this codebase. Valid at is when the fact became true. Invalid at is when it stopped. Created at is when Graphiti wrote it down. Expired at is when Graphiti stopped standing behind it. Same 4 roles, different spelling. And you will meet a 3rd spelling in the next system and a 4th after that. Learn the roles. The field names are only local dialect. Communities get built by clustering. And here, Graphiti makes a deliberate break with GraphRAG. Label propagation instead of Leiden. Why? Because Leiden wants the whole graph, and this graph never stops changing. Label propagation has a trivial dynamic extension. A new entity looks at its neighbor's community and joins whichever one the plurality belongs to. 3 votes left, 1 vote right, it goes left. Cheap, local, instant. The price is drift, so you still refresh the whole thing periodically.
Reading is 3 stages, and the paper gives them Greek letters, which we will not. Stage 1, search. Cast a wide net and find candidate edges, entity nodes and community nodes. Stage 2, re-rank. Reorder them so the good ones float. Stage 3, construct. Turn the survivors into a text string your agent can actually read. Search is tuned for recall, re-rank for precision, construct for the model. 3 different jobs, 3 different failure modes, tuned separately.
Stage 1 is not one search, it is 3, and they deliberately disagree. Cosine similarity over embeddings catches meaning, the paraphrase you would never have keyword matched. BM25 full text catches words, which matters enormously for product codes and surnames that embeddings smear together. And breadth first search catches context, things sitting near your hit in the graph, whether or not they read anything like the query. 3 nets with different holes.
Then re-ranking, and Graphiti hands you 5. Reciprocal rank fusion, for combining those 3 lists sensibly. Maximal marginal relevance, when you want variety rather than 5 phrasings of one fact. Episode mentions, which promotes whatever this conversation keeps circling back to. Node distance, which re-ranks by graph hops from a node you nominate. That is, how you say about Dana specifically. And cross encoders, which are the most accurate and by some distance the most expensive.
Stage 3 is where all this temporal work finally pays a visible dividend. The constructor does not hand your agent a bare list of facts. For every edge, it emits the fact and its valid from and valid to dates. For every entity, the name and the summary. So the prompt your model reads carries the fact and the window it held for. That is the difference between an agent that knows Dana ran Meridian and an agent that knows Dana ran Meridian until March.
Enough architecture. Here is the right path as you would actually type it. Construct a Graphiti client against your Neo4j connection. Build the indices once. Then, for each episode, call add episode with a name, the episode body, a source type, a source description, and, the important one, a reference time. That reference time is the anchor the model uses to turn 2 weeks ago into a date. Get it wrong, and every relative date in that message is wrong with it.
That one await is doing a frightening amount of work. Behind it, an extraction call, a reflection call, an embedding per entity, a resolution call, a contradiction check, and a temporal extraction. Half a dozen model round trips for one message, and you pay most of them whether or not anything contradicts, because you cannot know there was no conflict without going and looking. Part 2D called that right amplification. This is what it looks like with a stopwatch on it. And the read path, which is almost anticlimactic. Await graphiti.search with a question in plain English. Back come edges, and each one carries a UUID, a fact string, and valid at and invalid at when they are set. Then the genuinely useful trick. Pass center node UUID, taking the top results source node, and search again. Now the results are re-ranked by graph distance from that node. 2 lines to go from anything relevant to anything relevant about this thing.
2 calls finish the picture. Build communities runs the clustering we just talked about, and you call it explicitly. Communities are not rebuilt for free on every write, which is exactly the trade label propagation was chosen to enable. And to retrieve nodes rather than edges, there are search recipes. Take node hybrid search RRF, copy it, set a limit, hand it to the _search method. Extraction, invalidation, communities, retrieval. The whole pipeline in about 40 lines. Now the evidence, and we are going to be honest about it. The headline result is deep memory retrieval, DMR, the benchmark the MEMGPT team established as their own primary metric. 500 multi-session conversations, each with a question and a golden answer. Zep scores 94.8%. MEMGPT scores 93.4%. Zep wins, the abstract says so, and most write-ups about this paper stop right there. Do not stop there. Look at the 4th bar. The 4th bar is the baseline, where you simply paste the entire conversation into the context window and ask. That scores 94.4. It beats MEMGPT with no memory system at all. And on the smaller model, plain full conversation scores 98.0 against Zep's 98.2. Why? Because each conversation is about 60 messages. It fits. The authors say so themselves and call the benchmark inadequate. A benchmark your baseline aces cannot rank anything. So they ran a harder one, and this is the number that earns its keep. Long mem eval. Conversations averaging 115,000 tokens, with question types like multi-session synthesis and temporal reasoning. Against a full context baseline, Zep goes from 60.2 to 71.2%. Latency drops from 29 seconds to 2.5. And the context handed to the model shrinks from 115,000 tokens down to 1,600. 2 caveats, because a number without its caveats is marketing. First, one category got worse. Single session assistant recall fell from 94.6 to 80.4. Compressing a conversation into facts loses things. That is the trade, stated plainly. Second, and larger, they could not run MEMGPT on long mem eval at all. So the benchmark that proves something compares Zep to a baseline, not to the state of the art. Both tables are honest. Neither is a coronation. So, you can now name the library, install it, list its 4 objects, trace an episode through 5 steps, explain why it clusters with label propagation rather than Leiden, read both code paths, and argue about its benchmarks like somebody who actually read the tables. That is what it means to know a system, rather than to have heard of one. Next, in Part 2F, we do exactly this again, for 5 more of them. See you there.
If you like this video, please subscribe and share. Thank you.